Okay, today we have a pretty exciting, interesting class. We're going to be going in and around black holes and seeing what it's like there. We've done a little bit with this in previous classes. And also we'll be talking about later in the class gamma ray bursts and what they are, whether they're, how it is they, well, we don't know how it is they explode, but where they're seen well across the universe. They're tremendously powerful explosions that can be seen further away than any other explosion. So we'll talk about those a little bit. And in future weeks, we'll be going out into the universe even further and talk about galaxies and the universe as a whole. But first, you might contemplate what it is we're seeing. This is an illustration. This is not a photograph. But it's a really cool illustration that we picked out from a bunch of illustrations that were online at the Chandra X-ray Observatory site. And so we should try to figure out what it is we're looking at there. I'll talk about it later. But first, for the people who just are chancing across this, unclear as to what is going on, this is Physics 1600, Introductory Astronomy, and this is the 16th lecture in that series, and we're most of the way through, but not all the way through here. Black holes and gamma ray bursts today. Next time we're going to talk about our home galaxy specifically. So this lecture is taking place in the basement of Reiki Hall, attached to Fisher Building at Michigan Technological University. I am Professor Robert Nemiroff, and if you're taking this class for credit, which if you just stumbled across this on the web somewhere, then no, you're not. But if you're downloading this from the course web pages, you must already know that you go to courses.mtu.edu. And so what are you responsible for in this strange new world of online stuff? So you're responsible for the lecture material. Supposing I say it correctly, what I say and what I mean and not what I say. If there's any wondering about what that is, then send email to PH1600 at mtu.edu. It's the course. So you're responsible for the lecture and the Wikipedia entries, supposing they're correct. And if you edit it to change what it is, to put in what it is you want, then we will have to go back and look at what it was right in the beginning of the course. So far, no one's done that, as far as I can tell. The astronomy pictures of the day posted during the semester. So this course is trying to be one of the most beautiful astronomy courses, as well as the one of the most up-to-date, which APOD does pretty well. So if you're taking the course for credit, you should have already done quizzes 1 through 8. And to your delight, I am sure homework 9 will be released later today. An online quiz, find it there. Okay, so the Wikipedia entries today are black hole, event horizon related to a black hole, you might know. Photon sphere, talked about a little bit before. Einstein ring, talked a little about before, and as advertised, gamma ray burst. So let's get to the cool stuff. Oh yes, star death. So how is it we have black holes? Well, one way is it's the end state of a very high mass star. Exactly how high the mass is, we're not sure. It might even be dependent on how much metals are in the star. Metals meaning elements higher than helium. But a very high mass star will most probably go supernova in some way. It may leave a neutron star as a remnant, or the remnant might have been so dense that it overcomes even neutron degenerate pressure and becomes a black hole. The low mass stars we covered before. So here we're zooming in on this. So black holes have these attributes. A lot of slides right now. I haven't gotten to the cool stuff. They have, okay. One thing that's unclear is whether black holes are indeed singularities. So what is a singularity? A singularity, it was a general relativistic entity that has very specific things. But for the sake of this course, you might consider it to be a point, a single point of mass that has, let's say, a lot of mass. But it must be infinitely dense if it's just a point. So as we've found out time and time again in astrophysics, the extremums just mean you don't know what you're talking about. So if you say something is infinitely big, then you just don't know how big it is. It's bigger than your measuring rods. So to children, things are infinitely big. The Earth is infinitely big, but we know it's not. So a singularity is something that seems to be infinitely small. But it just really means, in my view, that we just don't know how small it is. All it has to be is smaller than something called its event horizon, and then it begins to take on the attributes of a black hole. It is essentially, in the general relativistic sense, a black hole. So what do I keep talking about this general relativity? Well, the most common theory of gravity that we use today is Newtonian gravity that was discovered and used by Isaac Newton back several hundred years ago. Essentially, Newtonian gravity can be summed up by this equation that's quite familiar. F is equal to gm m over r squared. So you have two objects, one of big mass m, one of small mass m, and the force between them is given by this equation. This works pretty well for almost everything we need to know about gravity. It works for satellites, it works for binary stars orbiting each other, it works for the Earth going around the sun. It's really the best approximation of gravity that we need. However, if you look really closely at, say, the orbit of Mercury, or even the orbit of the Moon, things tend to be a little bit different. Also, it turns out if you look very near the sun during a total solar eclipse, and if you look, you see deflection of background starlight that's not predicted by F equals gmm over r squared, because in that case, the mass of a photon would essentially be 0, and you wouldn't get any deflection, but you do. So there must be another theory of gravity out there. So Albert Einstein set about to discover this theory of gravity. And he came up with one theory of gravity in 1911. And it deflected, it predicted a certain amount of deflection by starlight. And so they were going to test it in around 1912, but they couldn't due to there was a total eclipse of the sun due to weather and things like that. So that prediction Einstein made in 1911 was wrong. So Einstein got several wrong theories of gravity before he got one that was a better approximation than Newtonian gravity. In 1915, Albert Einstein came up with general relativity, which is called GR for general relativity, and does better than Newtonian gravity in predicting things, but it's much harder to use typically than Newtonian gravity. So usually we just go back and use Newtonian gravity because it gives us all the accuracy we need. But to get to another level of preciseness with satellites, with light deflecting, we go to general relativity. And it is through general relativity that event horizon is clearly defined. It is possible to come up with an event horizon concept in Newtonian gravity. It's just where the escape velocity exceeds the velocity of light. And if you're willing to say there's Newtonian gravity is true, but the velocity, the speed of light is not infinite, then you can have an event horizon. But in special relativity, sometimes called SR, the speed of light is constant for all observers. So if you try to run and catch up with light, and then you look at it again, how fast it's going, you're not getting any it's not going any different, which is really, really weird. Special relativity is strange, and it took a generation of scientists, of physicists, to die before it became the completely accepted paradigm. So many people, many physicists who are alive, when special relativity was created in 1905, they went to their graves they believing it was too weird to be true. So generally, if you try to catch up with something, it's going to move slower. But Einstein said that's not what the data's saying. When you go as fast as light, or when speeds approach that, then things are different. It's only because we move so slow that we're in a different regime. So then the speed of light used to be infinite, but then Einstein said, back to the same theme, no, it's not infinite. Speed of light is finite. It's just faster than we can tell easily, but we can measure it if we go to a lot of effort. So once you put in place Einstein's general theory of relativity, it does itself predict that there is an event horizon. It also predicts that things would fall to a singularity, which is a reason why we think that general relativity is not in itself the ultimate theory of gravity. There is probably a more sophisticated theory of gravity which predicts that things don't come to a singularity, that they stop at some amount of quantum irregularity. But quantum mechanics, which is explains typically the very small, has not been put well together with general relativity. So for the sake of approximation, we just say, well, it's a singularity. But we don't think so. But the event horizon is less controversial. It does not, does not mandate a singularity to have an event horizon. Things can be pressed inside their event horizon. When something is inside, a piece of mass is inside its event horizon, light cannot leave it anymore. So this is light can't leave. So for instance, if we were to take the sun and compress it as much as you could, so we get everybody we know out pushing on the outer surface of the sun until it's compressed. Once we compress it down smaller than 3 kilometers, which is 700,000 kilometers in radius now, so we really have to do a lot of pushing. Once it gets inside of 3 kilometers, it doesn't matter what's going on in there. It could have nuclear explosions galore. Nothing's getting out, because the gravity is so strong that the light bends around and comes back rather than comes out. If, let's say, we just take an enterprise project of compressing the Earth, how much do you have to compress the Earth in order for the Earth to have an event horizon? Well, it turns out it's got to be about a centimeter or so. So maybe this is a centimeter on your screen. Maybe not. Maybe you have a super big screen. Pretend it is. So compress the Earth down to this size, this red dot, and no light gets out. So although things might be different on the Earth, everyone can turn on their lights and their stereos and their radios, and nothing's getting out. It's inside its event horizon. Okay, so we got that one. We got that one. On to photon sphere. So if you have something that has an event horizon, has been compressed inside its event horizon, like stars might do, very massive stars at the end of their lives, you can have a gravity so strong that inside a certain place, photons fall back. Outside a certain place, photons get away. But in the middle, photons, light, can do an orbit around the black hole. And when photons can do an orbit, that's called the photon sphere. Okay, we'll review these as the slides come by soon. So the next one, clearing this, is the Einstein ring. Okay, so this one's harder to explain. This is a gravitational deflection concept. So let's say you have a person here who's saying hi. Well, you can't read it. You have a black hole or something. It doesn't have to be a black hole, actually. It's very massive there. And you have a light bulb here. Light from this light bulb can go one way or it can go the other way to get to you. So that means if you're a human and you look along this path or you look along this path, either path you can look at, you can see the same light bulb. There's still only one light bulb, but looking along either of those paths, you can see the light bulb. So it turns out that the divider between these, there's a dividing line where, I'll make it a little bit bigger, where one image has to go inside the Einstein ring, another image has to go outside the Einstein ring. So another way to see it is if you put the light bulb, let's put the person back here, and we put the lens, could be a black hole there, and we put the light bulb back here. Let's have a new drawing. Now we directly make an alignment. So the eye of the person, the black hole, and the light bulb are all on the same line. Then all the photons will take the same radius, and when this person looks out, they will see the light bulb not as a light bulb, but as a ring. That is an Einstein ring. And the existence of that was also discussed by Einstein prominently in the 1930s, which is why it carries his name. Okay, time dilation. Very interesting fact about black holes. Let's see. So you have a big black hole here. And you have somebody standing near the black hole. Somehow they'd have to have a rocket jet on, and they have a clock here. And then you have somebody far away, and far, far away, as Shrek would have it, and they have a clock here. And what happens is, as you look at the clock, you see the second hand sweep around. Well, now, if you're far away, and you're holding this clock in front of you, you're far away from the black hole, you see this clock go around at a normal rate. Now let's say you're this person here and you're hovering near the black hole. Oh yeah, you'd fall in. So let's say you've got a hook from infinity, a big rope that comes from infinity and hooks into your belt and holds you there. You look at your clock. What is it that you see when you look at that clock? The surprising answer is you see that clock move just like it always has. You don't see any difference. That clock, second hand, zips around just as fast as it always did. No difference. The reason is because both you and the clock are at the same place, same radius from the black hole. Now let's do something different. Let's talk about this person out here looking down, not at his or her own clock, but at the clock that's near the black hole. What do they see of that clock? The photons climbing out of that, away from the black hole, come fewer and further between. And they're more redshifted. And so when you look at the black hole clock, the clock near the black hole, you see it running slow. And in fact, when you look at this person here, everything they're doing is slow. They're slowed down. That is time dilation. The opposite time dilation is if you're this person now hanging out near the black hole and you look at this person who's far away, they're moving real fast. Hey, what's going on? Let's go do stuff. They're zipping around real fast. And you look at their clock, it's zipping around. The second hand's going zing, 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 all around, around, around. That's the opposite kind of time dilation. Things are speeding up. So that gives one a way of thinking about gravity in a whole, particularly when gravity applies to light. You can think of the whole idea of gravity as places where time slows down. And because things tend to travel on paths of minimal time, things tend to fall toward them. That's one way you can think of general relativity. Many people think of general relativity as these rubber sheets where you push things down. Yeah, that works too. There's famous books on that. I kind of like to go with the photon way of visualizing things, that things slow down. But if you're right there with your own clock, it looks the same to you. Okay, black holes are strange. Here's a visual of what I showed before. This is the so-called singularity here. Means it's too small for us to understand. Too small for us to see because it's hidden for the event horizon. So if we tried to look and see if things were really a point, couldn't see it. It'd be inside the event horizon where things are dark. So here is the event horizon that forms around the supposed singularity. So inside of that, things are definitely dark because light can't get out of there. Here is the photon sphere here. And here's the strange thing. The photon sphere is what people think the event horizon is, in a sense, that it's actually dark everywhere. If you look at a black hole, it's actually dark everywhere inside the photon sphere. Because light can't come to you. Well, if light was to be emitted inside the photon sphere, it could come to you, but light that orbits inside the photon sphere zings in, spirals into the black hole. So every outside thing goes around the photon sphere. So actually, what you see is you can only see outside the photon sphere for a black hole. And I'm not sure what this one is. That's another circle. Not sure. Okay, so we went through this. So a lot of this is covered the other lecture. So let's say you had this cartoon of space right here. So there is a black hole, say, right here, but you can't see it because it's tiny little. Here's the belt of Orion. This is the star Sirius, brightest star in the sky. I think this is Betelgeuse here. Now, plop, put down a black hole. Well, here you go. Inside of this, you don't see anything. The inside of that is essentially inside the photon sphere. Now, again, if you can be lowered inside the photon sphere and then be pulled back out. So that can happen. So it is not the point of no return. But photons, if they try to orbit there, spiral into the black hole. Outside of here, you get the, let's see if I can find exactly where it is. It's about here. So this is the photon sphere. I ran out of space there because I have a little, you can't see it up there. This is the Einstein ring. And yes, technically there can be more than one Einstein ring, but we're not going to go into that. So images are reflected about the Einstein ring. So here's one image of Sirius. Here's another image of Sirius. Let's go to blue. Here's one image of the yellowish stars. This might be, I'm not sure if this is Betelgeuse. Here's another one. So they're on opposite sides. You can always connect them right across the center part of the black hole. All right. Are there black holes? Now, one of the things about newspapers is they're constantly reporting that black holes have been definitively discovered, and they wouldn't be constantly reporting that if they've ever been definitively discovered, because once they've been definitively discovered, you don't need to report it anymore. But no, sure enough, every year or so, there's another clear indication that black holes have been definitively discovered. So what's going on? The answer to that is that we don't have 100% knowledge that there is a black hole out there. We've never gone up to, driven a spaceship up to something that's a black hole and looked at it and dropped things into it and said, wow, cool. It's like dropping things off a building, you know, like, ooh, it fell in, wow, gone. You know, never get that back. But we look out in space and we see things that have attributes of black holes. They look like they could be black holes. But we don't know for sure. And as time goes on, we get better and better cases of things that could more and more clearly be black holes. Some things we see out in space that we think are black holes are just floating free in space. It's more easy to say that they're black holes, though, if they're part of a binary system, because they will have attributes then. We can better define attributes they have. They have a binary companion that's doing something. We can estimate its mass from that. We can estimate its radius because it's not larger than the orbital radius of the binary system, for one thing. In the X-ray band, we can see lots of X-rays come out on very fast timescales sometimes. And we think part of the reason for that might be that there's a black hole involved. Another possibility is that so these black holes up here, they tend to be roughly the mass of the sun. Put one solar mass there. In the centers of galaxies, there's also lots of evidence that there's black holes, and I'll review some of that pretty soon. So the Milky Way is thought to have a black hole in the center of our galaxy. It's called Sagittarius A star. And we would know it much better if it wasn't shrouded by lots of optical dust that's keeping us from seeing it in the optical. But we can pretty much see to it in other wavelength bands like the X-ray. So it's thought that many galaxies, though, have galactic nuclei that are black hole, and some have stuff falling into the black hole and creating spectacularly bright displays. And when that happens, we call it an active galactic nuclei. One example of an active galactic nuclei is a quasar, which is particularly bright in either optical or radio emissions. Okay, so here there's a lot of cool artwork involving this. This is a candidate black hole binary system, Cygnus X1. So here is the binary companion, a relatively normal star. This relatively normal star would like to be puffed out more than it is. But its outer envelope gets too near the black hole, and so it actually gets into a gravitational pulling contest between its mass and the black hole's mass. And if it's out too far, the black hole is going to win. So what happens is the stuff wants to go fall into the black hole. Well, why doesn't it just fall right into the black hole? The reason is because black hole is really small, and it's tough to shoot right at it. It's like hitting a bullseye at far away, so you're going to miss. Also, the binary system is rotating about itself, so where the black hole was isn't where it is now. So things tend to miss, and when they miss, though, they correct themselves, and then they start spiraling around, and so you get what's called an accretion disk here. I might be misspelling this, not paying close attention. Accretion disk. So in the center of this accretion disk is thought to be a black hole. But things can get very bright when you get near the black hole because the gas tends to collide with itself. And just like here, when gas tends to collide itself and become bright, fusion there, it heats up thermally over here. Okay, this is a black hole that was found because of its gravitational lens effect on background stars. So in this particular black hole candidate, this picture is by the Hubble Space Telescope. It's Wide Field Planetary Camera 2. It was found that here is a relatively dim background star. Here's that same star lit up. But it lit up in a very special way with a light curve. It became brighter and dimmer in a pattern that's just like a gravitational lens effect that we know about from our own solar system. And so one hypothesis is that something went in front of it. Well, let's look for the thing that went in front of it. Where is it? It must be really bright. Sometimes it is bright for gravitational lens effects, but in this case, it wasn't bright at all. It was really dark. So here we have something that was relatively massive and relatively dark, but it was essentially a point mass, essentially a compact mass that gravitationally lensed the star behind it. So one guess is that it's a black hole. Next, the center of our galaxy has several things that are so bright and so compact that we're guessing they're black holes, sometimes called the swarm. So all of these guys are A, B, C, and D. Okay, let's get rid of that color. Let's go to red. A, B, C, and D, these are all black hole candidates. So there's lots of black holes in our galactic center. But the most massive one that actually isn't labeled is this one, which is Sagittarius A star. Sag A star. Okay, okay, so one of the things that black holes are thought to emit, if you look closely here, right near the black hole, gas would be heated so high by colliding with itself that it would be emitting X-rays and flickering because some of it would fall into the black hole. So one way we can identify black hole candidates is by flickering X-rays. And so here we have a map of the X-rays near the galactic center, near the galactic core, and you can see a lot of unusual X-ray emission, and that indicates that there are black holes there. Okay, so there's other X-ray indications. One is that a star went too near a black hole. This is, again, an artist's illustration. This is not a photograph. If it was a photograph, we'd see a lot more gravitational lens effects, actually, right near the black hole. This star undergoes what's called tidal effects. So we see tides on the Earth. Tides on the Earth are caused by the sun and the moon pulling on the nearer part of the Earth more than the further part of the Earth, and that causes the Earth to get squished. Now, if you get near a black hole, you can get much stronger tides, and the pulling on the near side is much stronger than the pulling on the far side, and so it can actually pull a star apart if it gets too close. And when that happens, X-rays are emitted in a certain pattern, light is emitted in a certain pattern, and people think they're seeing this pattern with a star being ripped up as found by the Chandra X-ray Observatory. I think this might be near our galactic center too, I'm not sure. So one question comes up, what is the closest gravitational candidate? And that is V4641 Sagittarius. So I've got notes on this. This is 1,500 light years from the Earth. Is the closest well-known black hole candidate. Now, there could be a black hole in the outer solar system for all we know. It's not emitting a lot of light if it is, and it's not massive enough to deflect the light from background stars enough so that we can see. There could be a black hole only, 100 astronomical units away if it's really small. In fact, there have been really cool science fiction books and actually a movie now made of what would happen if you, some rogue scientist, scientists are always rogues in movies, I don't know why, but some rogue scientist decides to is a density freak, wants to go to the highest density possible and create something so dense it creates a black hole in the story's case, his lab. Could have been a her. So that's a problem. Okay, it's a micro black hole. It only has the mass of, many bowling balls or something, but it's a mini black hole. I guess it'd be a micro black hole. So as the story has, I think it's called the Crone experiment. Please take it out from the library so you don't think I'm advertising this to buy. Many libraries have it. Experiment. And Crone, I guess, is the guy who had the experiment. This thing starts falling through the Earth, going back and forth, creating strange anomalies. And so the major superpowers begin to think that the other superpower is doing strange things. And so there's a part of the book where they... And then it falls to the scientific community to try to save the Earth from being sucked into becoming just 1 centimeter black hole. And I won't spoil the exciting conclusion for you. But that would be, the closest black hole would then be, within meters sometimes. But the closest black hole that we have clear evidence about is 1,500 light years. And it's known to emit radio bursts, different explosions. It changes its color and its brightness within minutes. And it is thought that there are chunky things falling into, chunks of gas or something falling into this black hole that are causing that. Theoretically, it could be a neutron star. Okay, here's another interesting case, MGC 63015. I have notes on that too. So this is at a core of a galaxy, and it is making the core of a galaxy very bright. Again, this is a drawing. This is not a photograph. Again, they've ignored gravitational lens effects, or you'd see very strange distortions of things around here. So making it flat and Newtonianized, you would get these things falling in here. And the idea is that a black hole, if it has a magnetic field and is charged to some degree, can act like a battery. It can spew out some of the energy that's falling into it. The magnetic field can give it ways that things can come out. So they think that this might be this black hole, MCG 63015, is bright because it is transforming energy from the falling in energy of the accretion disk into energy that's falling out. And that's an interesting kind of research topic in modern gravitational astrophysics, trying to figure out ways of getting energy out of a black hole. Okay. We're out from around the black hole. So black holes do something called frame dragging too. So if you're rotating near a black hole, you won't think you're rotating. It's possible if you're in a specific frame, hard to describe, then, so if you're out, we can tell, way out away from things that are rotating, we can tell whether non-rotating gravity is working or rotating. So you can, okay, think about this. You can make fake gravity by creating a space station that rotates on its axis, as in the movie 2001. Who's seen 2001? Okay. In there, there's this thing that rotates, and then people who walk are pressed to the outside axis. And it looks very much like gravity. But there are clever ways of telling, like by spinning tops, telling that fake gravity from real gravity. But if you go near a spinning black hole, it will actually drag your inertial frame around to it. And then if you go around, you can see the background stars go around in circles, but you don't perceive that you are rotating at all. So that's a really interesting effect called frame dragging. Black holes, the disks around them can have certain, well, we won't explain this in too detail right now. This is an accretion disk phenomena. Black holes can create jets. Here's an X-ray jet. Black holes can also evaporate. This thing is made popular by, was discovered that they could evaporate by Stephen Hawking, a very famous astrophysicist. A very cool idea that actually black holes are not completely black. And that if there are virtual particles, there's a little bit of quantum mechanics in there. As virtual particles, some can fall in. So if you have a black hole, one virtual particle can fall in, its twin can make it to infinity, and the mass of the black hole goes down, and something escapes to infinity. So black holes can then have temperature. The more massive a black hole, though, the lesser its temperature. So very small black holes would be actually hot and emitting, really small black holes would be hot and emitting lots of radiation. So one of these black holes, these micro black holes emitted in the lab, might be actually emitting things like gamma radiation. Okay, here's a view of the galactic center. I don't think this is invisible light because we couldn't see this. I think it's in some sort of infrared light. And let's go back and forth. And you can see the stars moving around near the galactic center. And the closer you get to the galactic center, the faster they move. And so this wasn't taken in real time. This is the time-lapse image. So then we have to think, what is it that can be that small and that massive? It has to be small enough for the stars in the galactic center to move near it, It has to be massive enough, dim enough so that we don't see it. And the answer is, one clear answer is Sagittarius A star is a massive black hole, possibly on the order of 1 million times the mass of our sun. Not all galaxies are thought to have a single black hole in their center. The nearest major galaxy to our own, M31, is thought to have 2. And so it is thought that when galaxies collide, many times the 2 black holes in the centers of the galaxies then do a dance, eventually coalescing in a spectacular blast of gravitational radiation, which we won't discuss more about right now, a different kind of radiation than light. Light is electromagnetic radiation, so if you move a charge, you get light. But if you move any mass, you get gravitational radiation. So every time you move, you're creating gravitational radiation, but really, really little, small amounts of it. Very hard to detect. But if 2 major black holes start falling into each other, then you get a lot of it. Okay, so here's a big massive black hole, M81. It's a Messier object. And here's the center of it, a very active region that probably has a bunch of black holes and a supermassive black hole in its center. We're running late, so I'm going to go a little bit faster. Here's another one, 3C75, 2 black holes probably doing their merger dance. And you can see jets of hot gas shooting off of them. A really cool image. Here's another one, 2 cores. I've covered that enough, and I need to get to gamma ray bursts and apods, so I'm going to jump past that. Here's some active galactic nuclei seem to have single black holes, but this one in particular, NGC 4486b, also has 2. Okay, on to gamma ray bursts. Now, it might have something to do with black holes. It might be that the explosion, the supernova, that creates a gamma ray burst might leave a black hole in its wake. Gamma ray bursts are really interesting explosions. They were found by accident in the 1960s. So the US and the then Soviet Union were creating nuclear weapons. But each was wondering how advanced the other one was in creating their nuclear weapons. They have like lots of them, or are they just like not able to do much? So if you ask them, they just don't tell you. So one way to these nuclear weapons would have to be tested, and if they're tested in space, then they would emit gamma radiation. So the US launched the Vega satellites to test to see if we could see flashes of gamma radiation possibly coming from the then Soviet Union's nuclear explosions. So we discovered a problem, that there seemed to be a nuclear explosion occurring pretty frequently, as much as once a day. So that was intimidating. But then when they launched more than one satellite, they realized that these explosions were not on or near the Earth. They were at random positions far away on the sky. So far away, they couldn't tell how far. Essentially infinitely far away, so far as the satellites could tell. Well away from the Earth and the solar system. So then the military lost a lot of interest in them because they realized they were not having anything to do with the then Soviet Union setting off nuclear explosions. But astronomers became interested in them. Because this was a new kind of celestial event that we didn't know what it was. And so we've been studying them ever since, and we're still not exactly sure what many of them are. We do know that they last for seconds. And so if your eyes could see gamma rays, and it wouldn't matter if they could on the surface of the Earth because the gamma rays would be blocked by the Earth's atmosphere, but if you could just take away the Earth's atmosphere and your eyes could see gamma rays, both, and you were walking around, you would see a dark sky. Sky would be dark, wouldn't be stars in the sky. Pretty much. But then there'd be this tremendous explosion in some direction. Like, wow, like the whole sky just totally lit up in that one direction. And it would flash. It would become bright, dim in that direction. And then it'd be gone, totally gone. And you look back in an hour and say, oh, where was that bright explosion? Wouldn't be there anymore. And you tell your friends, look over there, there was a bright explosion there, and they wouldn't see anything. They'd say, no, you're crazy. So the next day, you'd be walking down the street, and there'd be a completely different direction. There'd be another bright explosion. And it would flash bright, dim, bright, dim, bright, 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 dim, 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 in a different sequence than the other one. And it turns out, about once a day, somewhere in the universe, there are these tremendous flashes of gamma rays. And those are the gamma ray bursts. And the reason they outshine the entire gamma ray sky when they go off. And we can see them from across the universe. We know now that they occur at cosmological distances, and we can see them further away than even we can see supernovas. And they might be more powerful than even the most powerful supernovas. They might be a type of supernova, too. So the instrument that observed the most of these was the Compton Gamma Ray Observatory, and the Batsy instrument on top of that, which flew on the Compton Gamma Ray Observatory, saw 2,704 gamma ray bursts, and here they are randomly shown on the sky. And the colors show how bright they are. Now we know there are at least two different types of gamma ray bursts. One, the first type is really short and usually lasts less than a second. And the other is relatively long and usually lasts for several seconds. Well, the neat thing about the short gamma ray bursts is we think those are caused by two neutron stars. Well, one leading model, let's say, for how short gamma ray bursts are created are two neutron stars that are orbiting each other, and they coalesce into one gigantic, well, more massive neutron star, or it becomes too massive and becomes a black hole. When this happens, these are tremendous amounts of neutrons being exploding and liberating, particularly if it's well, it is a gamma ray burst explosion. And these kinds of explosions might give the heaviest elements that are around. So the nucleosynthesis that goes on in stars and in typical supernova explosions creates a lot of the lighter elements like carbon. But when it gets up to the more massive elements like gold, for instance, it's tough to make that much gold in the cores of stars and in classic supernova experiments. So people think that one major hypothesis that the gold many people own as jewelry is a souvenir of these tremendous gamma ray burst explosions that involved lots of neutrons and created neutron-rich elements, high Z elements with lots of neutrons and protons. So we might have with us, many people might have souvenirs of some of the most powerful explosions in the universe, short gamma ray bursts. Here's another image like that. Here's just a computer simulation. A gamma ray burst might occur from a specific type of massive star, particularly one that's very low in heavy metals on the outside, for the long gamma ray burst. So the short gamma ray burst might be merging neutron stars. The long gamma ray burst might have relatively little metals in them. But this is a Wolf-Rayet star. Oh, let's go to a different color here. A Wolf-Rayet star. A massive one that's relatively low in metals might have tried to undergo fusion in its core of too heavy an element and exploded. And so here is a picture of a nearby Wolf-Rayet star that isn't all as clean enough to probably make a gamma ray burst. Okay, here is an echo. An X-ray rings expanding around the gamma ray burst. These X-ray rings are not actually at the source of the gamma ray burst. This gamma ray burst is in a far distant galaxy. The X-ray flux that came from this burst then hit our galaxy, and the dust in our galaxy, gas and dust in our galaxy, showed this X-ray ring. But it's one thing you can do with it is it can show you exactly where the burst was. Okay. Most recently, this year, early this year, there was a tremendously interesting gamma ray burst that occurred across the universe again. But this one was so bright and possibly beamed so close to us that for several seconds, you could have actually seen the optical counterpart to this gamma ray burst with your unaided eye. So if you knew where to look, you could have just been sitting there looking there for on the order of 10 to 20 seconds or so. You would have seen this really cool little flash. And well, you would have been looking further away than you could have looked in any other way. So when you go outside, you can see stars that are usually 100 light years from us. If you know exactly where to look, you can see the Andromeda Galaxy. Or if you go on Wednesday nights when we have the telescope out here up in Fisher Hall, you can see the Andromeda Galaxy, which is like maybe 1 million light years away. This was billions of light years away. Maybe 7 billion light years away, I think, is one estimate. And here with the telescope zooming in is what it looked like later. Okay, so here we come back to, this is a model for what a black hole would look like. So in this relatively accurate model, I think, you can see a jet coming off the black hole. You can see the relatively cool accretion disk out here. You can see it heating up to become, yellow hot as it got closer. It's white hot when you get close. The black hole in the center is so small you can't actually see it even on this scale. So you're looking down into the accretion disk. Inside there's a black hole you can't see shooting out jet. And this is, I think, a relatively accurate depiction of accretion disk around a black hole. And now I will get to the astronomy pictures of this week. And then I'll let you go. Okay, that's today's. So, did we do Haunting the Cepheus Flare? I thought, let's even go back one before that. Okay, maybe I got it wrong, but Merock's Ghost is a star here. You know, it's a galaxy there that's seen near a very bright star. And it's hard to clearly identify it because it looks like it's a ghost of this star. Ghost means that you get internal reflections in telescopes, and sometimes you think you see something, but it's not really there. It's just light bouncing around the telescope. But that's a real galaxy there. Okay, so here we have on October 30th, which I think is a Thursday. Yes, we should definitely be doing this one. This is the Cepheus Flare. So this is in the constellation of Cepheus, and there's cosmic dust that's around relatively young stars. So here's some stars. Let's go back to red. And so the dust takes some very unusual shapes, and so these shapes are reminiscent of Halloween, which just occurred during this past week. Halloween was actually an astronomical holiday. Halloween, many people don't know, is what's called a cross-quarter day, which should be occurring midway between an equinox, a day of equal day, equal night, and a solstice, a day of maximum day or night. In between those, there are cross-quarter days. Now, it's drifted so that Halloween doesn't actually occur directly between the equinox and the solstice. So it's drifted some, but still, it's based on that. Another cross-quarter day, by the way, is Groundhog's Day. So this is the Witch Head Nebula, which is reflecting off of the bright star, I think, Rigel here. Is that right? Yes. And so that star is reflecting off of this dust cloud nearby, and just so happens the dust cloud looks a little bit like Witch. So it's a Witch Head Nebula. We get sent these images of these a lot. Okay. This is leftover from a supernova remnant. This is the Veil Nebula, the eastern part of it, and some parts of it appear, particularly through different filters, much more blue than other parts which appear much more red. This portion of the eastern veil spans a half a degree, which is actually, the Veil supernova remnant is actually very large on the sky, 3 degrees, which is 6 times the diameter of the full moon. But half a degree, what you're seeing here is about the diameter of the full moon. So you need good enough binoculars to collect enough light to see this clearly. Okay, we've seen this image before, but I reran it because it was so cool. Hadn't been run in a while. So sometimes teaching this course inspires me to rerun things on weekdays. My rerun day is typically Sunday, where we run the best of APODs to freshen up the APODs. And many people haven't seen some of the best APODs from past astronomy images from past times, so we run them. These are spicules from the sun, and as I say, there are pipes as wide as a state and as long as half the Earth, filled with hot gas, moving 50,000 kilometers an hour. And so they're above the surface of the sun, and you can see a lot of these tubes here. Looks like carpeting, though. Okay, on to Mercurian rays, and the Messenger spacecraft buzzed by Mercury last month and took, again, pictures of the cratered innermost planet that haven't been seen before. So we're still discovering parts of Mercury. And in particular, took a picture of this rayed crater. So here's the crater. Here are rays. And it re-raised the interesting question, why are there so many rayed craters on Mercury and they don't exist on the moon? And so this is a topic. There are lots of craters on the moon, but there are rayed craters even on the moon, but there are not as many rayed craters on the moon as on Mercury. So the question is, why is that? And it might have to do with the lightness of the material underneath the surface, and it might have to do with the solar wind coming off the sun. We're still not 100% sure. Okay, the Hubble Space Telescope has been having problems. It's gone into safe mode. They're going to be launching the space shuttle to service it soon, but it came out of safe mode, out of not taking any images a week or two ago, my sense of time, and it was able to take with its wide field planetary camera 2 an image of two interacting galaxies. These are both ring galaxies. Here's this ring and here's that ring. And it's unusual to have one ring galaxy, and it's even more unusual to have two. These galaxies are colliding, and most probably this galaxy has been through the center of that one. And the tides this one created on this created this ring as well. Okay, so this brings us to today's picture of the day. This is a picture of Cassini, which is swamped, just flew right by Saturn's unusual moon, ice-spewing moon Enceladus. Probably mispronouncing that, Enceladus. So here, it's from only 1,700 kilometers above, it took an image that shows a very strange landscape. And so you don't see craters in this landscape. There could be ice particles rising from these crevices. We're not sure exactly which crevices show the ice particles. Some are known better. One thing, though, is that Enceladus is a great place to look for life and fresh water. And so one wonders where one could land a spacecraft on here. Because the terrain, you can see images the size of a bus. If a bus was landing there, it would be really small. So it shows this is not really very flat terrain. So it might be challenging to put down a space probe there that might search for ancient life or even modern life that might exist. We don't know it exists. That might exist on the surface or beneath the surface. Beneath the surface, there might be seas of water of this very unusual moon of Saturn. And that'll wrap us up to next week, where we're going to jump into the Milky Way galaxy. So I'll see you next week. Bye.